Okay, so what we're going to be doing now is talking about energy and calculations involving energy, including some unit conversions. So that's a good chance to review what we learned earlier this week. Now, energy, the word energy itself comes from the Greek of the ability to do work. Okay, so energy can do work. So gasoline possesses energy, so you can use energy to drive a motor and then do work with, an engine or things like that. But there's actually two kinds of energy, and when we're talking about energy, there's a kinetic energy. That's an energy associated with motion or moving objects. And then there's an energy that's stored energy. It's called potential energy. So if I take this cup and I hold it up here like this has potential energy because if I tied a string to it and put it on a pulley, right, as if came down, it could do work. So that's a form of stored energy. Now, uh, another place where we see stored energy is like behind a dam. We have hydroelectric dams, right? And what do hydroelectric dams do? We stash a bunch of water behind the dam. The water comes through the dam and through a turbine, which then creates electricity. Okay, so that's hydroelectric. So positional energy, potential energy could be positional energy. You could even have static electricity be a form of potential energy because there's causes fabric to cling together. So if you have two things that are separated, static can cause two things to come together. So when they're separated from each other, that's a type of potential energy. And in chemistry, the reason why we like to talk about energy is because chemical energy is the energy that's stored in what we call chemical bonds, or the attractions of atoms in a molecule towards each other. Okay, so when you burn things, you're releasing chemical energy. So gasoline is a form of chemical energy, lighter fluid. These are all types, or we have fuel cell cars, right? That the fuel cell, what the fuel cell is burning, those are forms of potential energy. The chemical energy is potential or stored energy. Now we do have a law of conservation of energy. So conservation of energy is just like the conservation of mass. If the energy that you had, if you can calculate the energy you had before, after the chemical process, the total energy will still be the same. Okay. Now we'll do an example of that. I'll talk about that in a second. Let's talk about units we use for energy. So there are two kinds of calorie units. Okay, these are the ones that people are most familiar with because we think about when we eat food, we're consuming calories. Those are what are known as a dietary calorie. That's this guy here. Okay, and then there's the calorie that we use in a lot of scientific calculations, and it's just this one here. It's a cal. Okay, and there's a relationship. There's 1,000 cals, little cals, and one big cal. So a big calorie is actually also known as a kcal, like this. What is a calorie? The old definition of energy, like the first real definition of an energy unit was the calorie. And what they did is said the calorie is the amount of energy that it takes to take 1 gram of water. So you have a little cube of water, right? At least conceptually, a little cube of water, 1 gram. If you wanted to change its temperature by 1 degree Celsius, the amount of energy that would take would be called a calorie. Okay, so a little, like, remember, a gram of water is about a milliliter of water because the density of water is 1. So a gram of water raising its temperature 1 degree Celsius, that quantity of energy got to be known as a calorie. Okay, so now a kilocalorie, or a dietary calorie, that's what this is actually 1,000 of those calories. And the more modern unit that people talk about is the joule, right? A joule is related to the calorie in the sense that there are actually 4.184 joules in the little calorie. So a joule is actually a smaller unit of energy, more finely divided unit of energy than the calorie is, and then the dietary calorie is a big giant thing, okay? So The other way that you hear about energy is on your electric bill. And in your electric bill, there's something called a kilowatt hour. I don't know that it's really important for you to understand exactly what a kilowatt hour is, but a watt is a joule per second. Okay, so this is what a watt is. So like when you see a light bulb and it says it's 100 watts, it's actually burning 100 joules per second. Okay, so that's a 100-watt light bulb, 100 joules per second. Now, if you had 1,000 joules per second and you did that for an hour, okay, in an hour there's 3,600 seconds. So if you had 1,000 joules per second and you are doing that for 3,600 seconds, it comes out to be this number here. That's the number of joules that get burned. So a kilowatt hour is what you, like I said, you see it on your energy bill. It's basically a measure of how much energy you burned in your household. Okay. Now I talked through some of these, right? I talked about the cal and the kcal. Just a couple of notes that are important, right? The calorie, the dietary calorie, is always written with an uppercase C. Whenever you look at food, regardless of how they write it, that's a dietary calorie. So, for example, the Snicker bar that you might have eaten or the M&Ms that you might have eaten, those possess roughly 150 to 250 dietary calories, but that's 100,000 to 250,000 energy calories that we talk about when we're talking about like burning fossil fuels or those kinds of energies for calories. So it's actually in food there's quite a bit of energy, stored energy, chemical energy that we use when we eat it. Okay, or actually when you eat Snickers and M&Ms, they're probably not doing much good. But anyways, that's okay. It's emotional good. All right, so let's look at a couple of conversions. The conversions are done very much the same way. And we're going to be dealing with the kilowatt hour just because it's the hardest one, but the conversions are done very much like we did earlier. Let's say you had 25 kilowatt hours and you want to convert it to joules, right? So I want joules. I'm going to start with 25 kWh, and then I'm going to find my conversion factor, and it's the one that's up here. Normally I look them up and write them, but it's this one. 1 kilowatt hour, right, is 3.6 times 10 to the 6 joules. So 1 kWh is 3.60 times 10 to the 6 joules. And so this will cancel, and then we can calculate our answer. And I got 9.00 times 10 to the 6 joules. Okay. Now this one's a little bit more complicated because I have to go from calories to joules and then to kilowatt hours. The map, let me write this out, a calorie, right? And you're wanting to go to kWh, and we're going to go look at the units up here, right? And I have a cal, right? Let me erase what I wrote up here, or write it in a different color. I have a calorie, I can go to a joule, and from a joule, I can go to a kilowatt hour. So I'm going like from here to here, and then from here I'm going back over to kilowatt hours. So let's go ahead and use those and set up the problem. Get back to my blue pen. And it's going to be, again, I want kilowatt hours, so I'll write that here. 113 calories. And then I know there's 4.184 joules per calorie. And then I also know that the calories will cancel. I know that there's 3.60 times 10 to the 6 joules for every 1 kWh. And I'll calculate that value. And that should be 1.31 times 10 to the minus fourth, and then the units kWh like that. And then kilojoules to calorie. You'll often hear kilojoules. It's a common energy unit. So you'll notice there is up here, there's not a kilojoule on this table, but that's one of our prefix conversions, right? So the conversions that I'll need to know, I'll need to say that 10 to the third joules is a kilojoule. I just used the definition of K, right? Or 1 times 10 to the third joules is a kilojoule. And then I also know that there's 4.184 joules equal to 1 calorie. So those are my two conversion factors, because I can go from kilojoules here to joules, and then from joules I can go to calories. Okay, so I'll start with, again, I'd like to write what I'm looking for. I'm looking for calories, and then I'm going to start with the number that's given. And then if you want, we can do railroad tracks. I think it's a little neater sometimes. And then I'm going to say there's 1 kilojoule is 1 times 10 to the third joules. And then I have 4, then the kilojoules will cancel, right? 4.184 joules for every 1 calorie. And I'll let you finish this calculation, and we'll sort of move on from there. The next topic to cover concerning energy that we'll need to cover is the idea of temperature. What is temperature? And it turns out temperature is a measurement of the movement of molecules in a container or a system. So like a solid, like when you feel something that's hot, it actually means the molecules or atoms that make up that solid are actually moving faster at a higher temperature and slower at a lower temperature. So it's actually a form of kinetic energy. Now, there are different temperature conversions equations and different temperature scales, and so I'm going to go over those very quickly, but this will get covered all semester long, so it's something you'll be practicing as we go on. You'll definitely need to be able to convert some units over for the upcoming exam, okay? But let's go ahead and just write out what these equations are. The relationship between the Kelvin scale, okay, is you take the degrees Celsius and you just add 273 to it. Now, for Celsius to Fahrenheit, there's a couple of different versions. I kind of like the one that says that the degrees Fahrenheit is equal to 1.8 times the degrees Celsius plus 32. Now the 32 is the freezing point of water, okay? So that if you can remember that, that helps you remember the equation and sort of its origins. But these will be given to you on the test. Now, they're not rearranged for you on the test, so that's something that you'll have to do on your own, is rearrange equations and use them for calculations. So let's think about this. If you want to go from Celsius to Kelvin or Kelvin to Celsius, you only have to use the one equation, right? Because you have a direct relationship in this equation between those two variables. The same is true between Fahrenheit and Celsius. There's just one equation. I mean, you have to rearrange it and plug numbers in, but there's just the one equation. So Celsius to Fahrenheit's one equation, Kelvin to Celsius is one equation. But if you want to go from, let's say, Kelvin to Fahrenheit, you're actually going to have to use two equations, do two separate calculations. Now, my advice to you when you do that is if you have to go from Fahrenheit to Kelvin, don't round. Because you have a tendency to want to round numbers off. But you know, if you carry like a few extra significant figures, you'll always be safe. So any of these kinds of conversions, Kelvin to Fahrenheit, Fahrenheit to Kelvin, you're going to end up using both equations. Okay, so let's talk conceptually a little bit about what the temperatures, how the temperature scales are related to each other. So I have the three scales sort of drawn out here. This is for 10 degrees in Kelvin. Okay, so this is 10 degrees here. And this is this, sorry, there's no degree in the Kelvins. symbol. And then there's 10 degrees Celsius, right? That's this here. And the thing you'll notice is that the Celsius degree, so these measure the number of degrees going up here, right? The degrees are the same size. And that's why the equation looks like this. If you just want to know what the Kelvin temperature is, you just have to add a constant to it. Now, if you look at the Fahrenheit equation, it actually says something that's different. There's 1.8 degrees Celsius, right? 1.8 times degrees Celsius gives me the equivalent in Fahrenheit. So where this change from 0 to 10 degrees Celsius is exactly the same number of degrees change in Kelvin, right? In the Fahrenheit scale, it's actually 18. This is 18 degrees Fahrenheit. So what that means is there's 18 degrees in the same energy spacing as there are 10 degrees in the Fahrenheit or the Celsius scale. So the Fahrenheit, the degree Fahrenheit is actually a smaller unit. It measures a smaller energy change than the Celsius scale. And the Kelvin and the Celsius scale, the energy changes per degree are the same. Okay, so let's go ahead and do a couple of conversions. I won't do all of these, but I will do a couple of them for you, and then I'll just give you the answer for the last one, okay? So, and then you can practice and make sure you can get that. That's why there's no space down here. Okay, so let's say I want to go from minus 48 degrees Celsius to Fahrenheit. So I got to pull my equation out, right? So that's this one here. And I'm going to plug in my numbers. So let me write it down. It's degrees Fahrenheit is equal to 1.8 times the degrees Celsius plus 32. So that's my equation. So to do the calculation, then all I have to do is plug it in and make sure I type it in correctly in my calculator. So degrees Fahrenheit equals 1.8 times minus 48. So you got to be careful. That's a negative 48. We say minus, but really it's a negative. And get rid of the Celsius. We don't write any of these units in here. Plus 32, and that'll come out in Fahrenheit. So I'll pop that into my handy dandy calculator. You recognize my calculator, right? I tell you guys don't use these, and that's what I do all the time. So that gives me minus or negative 86.4 plus 32. So let me just add 32 to that. And that ends up being minus 54.4 degrees Fahrenheit. Yeah, pretty cold. It's like Minnesota in the winter. Maybe not quite that cold, but it can be. It's very cold there sometimes. All right. Now let's do the Kelvin to Celsius. So I know from looking at the equation above that Kelvin is equal to degrees Celsius plus 30, sorry, not 32, 273. Now you'll see different versions of this. This is just rounded to the whole degree. Sometimes you'll see 0.15 there. Just use whatever you're given, like when you're given a test and you have to take a test. You can look at the cover page for the exam. It's already been posted. You can take a look at that. It just sort of sits on the website the whole time. So let's go ahead and do our calculation. Okay. Now, I want to solve for Celsius, right? So I need to have a degrees Celsius equals. That's what I'm looking for. That means I have to take this equation and rearrange it. So I'm going to end up with Kelvin minus 273. I'm going to leave the 0.15 off. So that's going to be 273 minus 273. And I'll let you do this math, right? Comes out to 0. So 273 Kelvin, we don't usually say degree, 273 Kelvin is the same as 0 degrees Celsius. Now that's cold, that's the freezing point of water, right? So it sounds like it's a lot, but it's just because the scale has been shifted from the Celsius scale by 273. And actually when we talk about gases in about 3 weeks, we'll be discussing like why we have this number, okay? So before I move on, I'll go ahead and do this calculation off screen, and I'll just write the answer there so you have it. in your notes. So that's going to be your answer. Go ahead and try to do the calculation. You're going to have to rearrange the equation, right, and solve for degrees Celsius and then plug in the Fahrenheit. You should get your answer. All right, so temperature change and energy. So think about, it's kind of an interesting example. Hang on, I'll be right back. All right, so there's a little bit of a story to this. So here's a stick, right, chopstick, of course. And then this is a fork. And I'm going to do this little experiment. I hope it works. The ceiling fan's on, so I can stay cool in here. It's actually for my computer. If I don't blow air on it all the time, it gets super hot. Let's see what happens here. All right, so here's a match that's lit, right? If I go like this, a lot of you will know this, and then I go like that, right? It's not very hot, right? What's going to happen when I do this? And then I touch that to my skin, right? You guys kind of know what's going. I'm not going to do it. It gets really hot. But you notice I held this and this for the same amount of time. But the wooden stick. Ooh, I just threw that on the table. All right. The wooden stick, the chopstick, didn't get very hot, whereas the fork got really hot, right? And I could have burned myself. That's how they brand things, right? They heat up a piece of metal in a flame, and you can touch it to something, and it'll make a scorch mark. So there's a guy in Scotland who wondered about these things too. His name was Joseph Black, and he realized that it took more energy to heat some things up and less energy to heat other things. And really what he was thinking about is why in Scotland was the temperature so constant near the coast? And he came up with this idea of latent heat or heat capacity, the ability to absorb energy as something heats up. For a metal, the heat capacity is low, so it only has to pick up a little bit of energy to get really hot. Whereas for something like wood or insulating materials, right, the heat capacities are really high. It takes a lot of energy to heat these up. And it turns out water has a very high heat capacity. So if cold wind comes across the ocean and hits Scotland, the thing that it has to do to freeze the coastline, it actually has to freeze the ocean first. It has to cool the ocean down, and it's just almost an impossible task. If you go to the Bay Area, I think you've probably noticed in San Francisco on the peninsula, it's always kind of nice temperature and sunny, right? Except for when it's foggy, right? But anyways, that's because of the high heat, what we call heat capacity, and it used to be called latent heat, or that came from the term latent heat, of water that surrounds the peninsula. It's sort of another interesting side story. When I was visiting Scotland, actually, I went to Edinburgh University and visited there for a little while. And while I was there, they unburied Black's laboratory. They found it under a parking lot by the National Museum, and apparently it was just stuffed full of garbage. And they dug it up. And apparently this has been going on for years. Like when they have a spare room, and they're done with it, they would just shove junk in it and then bury it. Anyways, Joseph Black. All right, so let's talk a little bit about what his ideas, right? There's a thing called the specific heat, and this is often known as the MCAT equation, right? Because it looks like MCAT. And the MCAT is the test that people take to get into medical school. So we have different components to it. We have the heat, that's Q, which will be in either calories or joules, depending on the form of the specific heat that we use. We have the mass of the object, okay? So this is going to talk about this. And we have the change in temperature of the object. So think about this. If you have a lot of something, right, the mass is big, right? It takes a lot of energy to heat it up. If you have a very high specific heat, then it takes a lot of energy to make the temperature change, right? So these things are all interrelated to each other. The mass, the specific heat, the change in temperature, because if you want a big change in temperature, you're going to have to have a large amount of energy that goes into that process. So for water, the specific heat is, I should say, in calories, and this is not coincidental, specific heat of water in calories, 1.0 energy calories, not dietary, calories per gram degree Celsius. So what does that mean? It means if I have 1 gram of water and I want to change its temperature 1 degree, see this would be 1 and this would be 1, then the energy that's required is 1 calorie. And that's where calorie originally got its name. It's the amount of energy it took to raise that temperature 1 degree. Now, since, I don't know, since that time, really, there's still, like, I teach a lot of organic chemistry, and we still use calories and kcals a lot. But primarily what people use is joules, and if you remember, the conversion between joules and calories is 4.184 joules is equal to 1 calorie. So the equivalent to this is 4.184 joules is it's 1 grams per degree Celsius. These are both forms of the specific heat of water. Okay, so we see C and then we can use W as a subscript. Metals have very low specific heats, so it's very easy to heat them up. It takes a small amount of energy to get a very large temperature change, right? So let's go ahead and look at some specific heats. And I think what you'll notice for aluminum, it's 0.895, carbon's 0.58. And you notice going down this list, there's almost none that are even very close to each other. So it turns out if you can measure the specific heat of an object and it's a pure substance, now this is pure substances, right? This list is all pure substances. Oops, sorry. You can identify it. You can get an idea of what that substance is. Usually you would take a couple other types of measurements, but the specific heat is specific for that substance. So I didn't leave enough room here, but it says how much heat is required to raise the temperature of an 85 gram sample of water from 32 to 65 degrees Celsius. And it's actually a problem 71 out of 3rd edition. I don't remember if I assigned that one. Now, here's your problem strategy. There's a lot of information in these problems. So what you have to do is I generally write everything out. Q is equal to MC, and delta T is the change in temperature, right? So I keep talking about a change. We define that as the final temperature minus the initial temperature, like that. So if I want to do this calculation, what I often do is I write down the numbers under each one, or I'll write it out like this. I'll write Q, M, C, and I'll do T final and T initial like this. Okay, and then I'll read the problem. It says, how much heat? Now Q is the heat. So this is what I'm looking for. There's an 85 gram sample of water, and it's going from 32 to 65. So 32 is your initial, and 65 is your temperature, Celsius, is your final. And C, because it's water, right, you have to go back up to here and you have to look up what the specific heat is. Now, water has different specific heats depending on whether you're talking about the solid, liquid, or the gas. We're most likely at these temperatures talking about liquid water, so it's 4.184. It's this value that's right here, sorry. So this is 4.184. And the units are joules per gram degree Celsius. So now I'm all set. I can do the calculation, and I know that I'll end up with Q. Now, let's say it had been M instead, right? Then I would have had to solve the equation for M, and then I would have to do the calculation once I rearrange the equation. And like it says here, is you write the specific heat equation. Under each variable or in a column next to it, you write the given information. You usually have to look up the specific heat. You solve the equation for the desired variable. That means you want that variable on the left by itself, and then you calculate and check your work. Okay, so we're going to go ahead and say Q is equal to, now my mass is 85 grams. It's 4.184 joules per gram degree Celsius times 65 degrees Celsius minus 32 degrees Celsius, because delta T is T final minus T initial up here. I pointed to the screen and you can't see my finger. There you go, it's right there. So I'm going to plug that into the equation, and I did it already. It's just down below there, so I wouldn't have to spend too much time. It's 1. Well, so let me just write out what comes out of most of your calculators. 11736 joules. Now, the answer should have 2 sig figs, because this is 2 sig figs, and this will give a result that's 2 significant figures. So I'm going to round it to that place, and then you're left in that sort of weird situation of, do you write it as scientific notation? Do you leave a bunch of zeros? And I would prefer, if you have that many digits, like more than 3, maybe more than 4, you just do it in scientific notation. So this becomes 1.2 times 10 to the 4th joules, like that. Okay, that's rounded to the correct sig figs. Let's do one other, right? And actually two others. But I'm not doing this one that's the bottom. You'll notice this answer is here, by the way. So when you download the notes, you can cover that up and work it all out. So I have Q. This is an MCAT problem. Q is equal to MC delta T, like that. And it says 89 joules. Okay, so now, again, like I said, you could write it out on the side or you could write it underneath. I think probably since I wrote these notes, I sort of decided, gosh, it's a lot easier just to write them to the left like that, because then it's all in column form. But it says 89 joules of heat, so this is 89 joules. Gold coin, so that's 12 grams. Okay. And then I have C and delta T, and then remember, specific heat is specific to the substance, so I'm going to go up here and I'm going to look at gold, which is AU, but I think they say gold here, yeah? Yeah, alphabetical, so 0.129 joules, the units are up here, joules per grams degrees Celsius. So 0.129 joules per gram degree Celsius. Now, I need to find delta T. So that means I have to take this equation and I have to solve for delta T, which means dividing both sides by MC to get rid of the MC. So we're going to say delta T is equal to Q divided by M and C. Now you notice I didn't do T final minus T initial in this equation, because when I read this, I read temperature change. I didn't even think about it. I just wrote delta T rather than doing T final minus T initial. Now, when you do that, you'll plug in all your numbers, right? This will be 89 joules. The mass will be 12 grams. And the specific heat would be 0.129 joules per gram degree Celsius, like that. And then it'll come out to be 57.4935 degrees Celsius. Now, how many sig figs? Well, you're going to have 2, right? So you're going to round it to 57. This is one of those weird rounding ones where you have a 9 here, and what a lot of people want to do is round the 4 before they round the 7, right? And if you do that, you'll end up with 58. So you have to be careful. Again, this one's worked out as well, so I'll let you figure this one out. But this is kind of a different problem. I want you to look at the way this problem is worded. It says an unknown metal is suspected of being gold, right? When 2.8 joules of heat are added to 5.6 grams of the metal, its temperature raises by 3.9 degrees Celsius. Are these data consistent with gold? Now, this is an MCAT equation, right? So you're going to think about it like this. Q, right, is equal to MC delta T. And it gave us the delta T. It gave us the joules. It gave us the M, right? And the only thing that you don't have is C. So in this particular problem, they don't say it, But if you want to compare and see if the data are consistent with gold, you have to compare the specific heats. And so what you're going to do is you're going to do this calculation, right? And then you're going to compare it to the specific heat that we did here, because this was gold here. And when you do the problem, what you're going to find is that the specific heat comes out to this. And that actually is the same as 0.129 when you only have 2 sig figs, so you have to be a little bit careful. So the data are consistent with gold. Okay. And the last problem I want to do is this one. So I'm going to take a short break so I don't go like off into hyperspace, and we'll come back. When I come back, we'll do this problem. Okay, so let's think about what this problem says. Let's read it, and then I'll sort of sketch it out, and we'll talk about how you do this problem. It says a marble is added to 40 grams of water. The initial temperature of the water was 25 degrees Celsius. The final temperature of the water and the marble is 22.2 degrees Celsius. So here's the question. Did the marble gain or lose heat? And the second question is one that appears to be like very difficult to solve, but it's actually not that bad. It says, what is the heat change for the marble? So we want to know what Q is for the marble, right? So we're going to use conservation of energy to solve this problem. So think about, I'm going to make a beaker here, okay? So here's my beaker. And we're going to, that's a weird edge to my beaker, but it's fine. And then I'm going to put my marble in here, right? And the water was at 25.0 degrees Celsius, right? And the final temperature of the water in the marble, it went to 22.2 degrees Celsius. So what happened when that happened, right? Well, if the temperature goes down, what it means is it has less energy. So where'd the energy go, right? Well, the energy went into the marble. So the marble actually gained energy, right? And pulled it from the water. So it must have been at a colder temperature. We don't know what the temperature is, but here's the thing. The marble gained energy. In essence, I don't know if you've ever seen these little drink cubes. You can get a little stone. They're actually for like whiskey or something. You can get a little stone, and you stick them in your freezer. And because people who drink whiskey don't like to water it down, you could just take one of these stones and stick it in your whiskey, and it'll cool it down without adding water to it. Apparently, this tradition goes way back when they used to keep stones in the river in the cold water, and they could pull those out and cool their drinks with the cool stones. Okay, I don't know if that's true or not. That could all be like Snopes material, but I don't know. Anyway, that's what I was told. So 25 degrees Celsius goes to 22 degrees Celsius. The water energy went down, but conservation of energy says that energy had to go somewhere, so it must have gone into the marble, okay? So did the marble gain or lose heat? It gained heat. Okay, so now what we're going to do is we're going to do this. We're going to calculate how much energy it gained by calculating how much energy the water lost. So let's look at the information here. I have Q is equal to MC delta T. And look at the information that I have for the water. Oh, sorry. I think I accidentally moved my recording screen a little bit. Q is the question mark, right? And then M, where the water is 40 grams. C is water, so we'll have to look that up, but that's 4.184 joules per gram degree Celsius. And then delta T is actually T final minus T initial. So we're going to write both of those out, and we're going to look at the values that we got. So we say the final temperature of the marble, so that's the final, right? That's 22.2. And the initial temperature is 25 degrees Celsius. So I'll write 25. So I'm solving for Q. The equation's already solved for Q. So I just have to plug stuff in, right? So I'm going to say Q is equal to mc delta T. So this is going to be equal to 40, right, grams times 4.184 joules per gram degrees Celsius. But what's my change in temperature, right? So delta T is equal to T final minus T initial. So I'm going to have 22.2 degrees Celsius minus 25.0 degrees Celsius. And you're going to get a negative number. So that's going to be 2.8 degrees Celsius negative. Now, what does that mean? The temperature went down, right? It says in the problem, right? The final temperature of the water was 22.2 degrees Celsius, so it was lower in temperature than it started. The negative is telling you that it went down. So now I can plug that number in as negative 2.8 degrees Celsius. And then I can do my calculation, and notice how the grams will cancel here. The degrees Celsius will cancel here. So that's going to be equal to, and so if I did my calculation right, that's 468, negative 468.6 joules. So what does that mean, right? This is the energy change for the water. The negative means it lost energy. And that means the energy that's gained by the marble is going to be this. Because conservation of energy says whatever the water lost had to have been gained by the marble. And so all you have to do is you change the sign to say that the marble gained the energy that the water lost. If the water energy had been positive, that means the water would have heated up. And then the loss of energy in the marble would have been negative. So if you'd taken a hot marble and stuck it in the liquid, it would have heated up the liquid. But then the marble's temperature would have been high going to low, so it would have lost energy and would have had a negative energy change. Okay, so that's sort of it for this chapter 3. The next chapter will be chapter 4, and we'll go to 5 on Friday. So, again, you've got my cell phone number. Many of you are texting me, and it's making life real easy because I don't have to type as much. I just sort of dictate whatever I need to say. But feel free to contact me if you have any questions.